bar magnets. So the purpose of this lab was to measure the distance dependence of the magnitude of a magnetic field of a bar magnet, and then to compare these measured distances to the distances predicted by the Biot-Savart law. And so the fundamental principles here are the Biot-Savart law, sorry if I'm saying that wrong, which predicts the magnetic field of a dipole, and we're treating the bar magnet as a dipole here, and the distance dependence of the magnitude of the magnetic field, where K is a constant. So there were two parts of this experiment. First, we lined up the ruler and the bar magnet east to west so that it was orthogonal to Earth's magnetic field, so that Earth's magnetic field wouldn't be responsible for any changes in magnitude. Then we located the position of the magnetometer chip in the phone, and first we measured the distances required to generate given values of the magnitude of the magnetic field at different points along the axis. And then the system for this was a bar magnet, and the surroundings was everything else. And so this first part, as you can see, we measured the distances it took to generate a magnitude of 20 amps per meter squared, 70, 120, 170, 220, and plotted the natural log of the magnitude of the magnetic field versus the natural log of the distance along the parallel axis. For the second part of this experiment, we moved the phone to the parallel distance required to generate a magnetic field of 100 in magnitude, then moved the phone up by the same distance and calculated the magnitude of the magnetic field in each component. And so using this data, we were able to calculate n, which is equal to the slope, k, which is equal to, well, the natural log of k is equal to the y-intercept. And so using this as k and n from the distance-dependent formula, we can equate that to the formula for the magnitude of the magnetic field along a parallel dipole, and used that to find mu. And so mu ended up being 2.66 for this experiment. So using this data, I created, a computational model for the magnetic field of a bar magnet, which we're treating as a dipole. And so here I used the value of mu that we calculated from our experiment to set up the magnetic field, and created a function of the magnetic field of a dipole, and then set up 6 different observation locations, with 2 of them being along the axis and 2 of them being perpendicular to the axis. And using the function for the magnetic field of a dipole, created arrows showing the magnitude and the direction of the magnetic field at each of these points on and off the axis. And so this is just drawing the arrows at one for 45 degrees as well. And so this is what it ended up looking like, which is at least visually consistent with what we would predict from the Biot-Savart law. And so I did want to say some potential error that could have gone into calculating the dipole moment are, if the magnet wasn't perfectly aligned with the Earth's axis, then that would be interfering. And also, we probably didn't perfectly locate the magnetometer chip in the phone. So, quick discussion. If we hadn't oriented, and this is kind of the error I talked about, to compensate for magnetic north, and the meter stick was at a different angle, then Earth's magnetic field would also be changing the result, and so we would have to treat Earth's magnetic field as another field and subtract that from the results we were getting if we wanted to find just the bar magnet. And if we stuck 2 identical magnets together, then we would have double the magnetic field, theoretically. And yeah, that's that.